Welcome back. As we said before, it's time to add the region column. You can find all the region column specifications in the document you have. Now, HYSYS has nothing called region column, so we will add a distillation column. Here, double click on it. It's a very simple column with one ideal stage equipped with a reboiler, so it's a reboiler here, and a condenser here. It's a full reflux, and now the water will be separated as steam, so I'll name it free water 3, and the bottom outlet we have added it before, which is the region bottoms, which is connected to the heat exchanger. Also, you can add the inlet stream, which is the region feed, of course, to stage number 1, because we just have one stage. Then next, the condenser pressure, we have it in the table, 101, and the reboiler pressure, we cannot change it because we have already, the reboiler pressure drop is recorded as 0, so we have to remove this. Then it's time to add the reboiler pressure, which is 103, and the condenser pressure drop, which is 2 kilopascal. Next, we do not have temperature estimates now, we do not have reflux ratio now, so it's done. Go to monitor. As you can see here, we need 2 specifications. To have a degree of freedom of 0, we have to define 2 specifications. I'll deactivate these 2 specifications. We will add two confirmed specs and add another 2 that we know, but as estimates. The first one is the condenser temperature, so add specs, the column temperature, here, double click on it. I will call it condenser temperature, stage, of course, condenser, and the value here is 102 Celsius. I'll do the same with the reboiler, column temperature, I call it reboiler temperature, the stage is reboiler, and the value 205 Celsius. Now, I want to add other mole estimates, which are the reflux ratio, it's here, reflux ratio estimate is 1, and steam draw rate, which is overhead vapor rate, to be 1 kilogram mole per hour. Now we have already activated these 2 ones, and the first 2 are estimates. Let's run the column. Yeah, the column now is convergent. As you know, there is no real process in the world without losses. I'll zoom out to see the process in general. So, some triethylene glycol has been lost with the triethylene glycol from here, which is the region bottom, has been lost with the free water. We want to make it up, so we will add another stream from F11, and we will call it triethylene glycol makeup. The temperature 15 degrees Celsius, and the composition here, mass fraction, do not forget, 1% H2O and 99% triethylene glycol. Now we will mix this stream with lean from lean rich heat exchanger through a mixer. This is the mixer. Double click on it. The ends are triethylene glycol makeup and lean from lean rich heat exchanger, and the outlet is triethylene glycol 2 pump. Do not forget to go to parameters and equalize pressures. Now we want the rate of triethylene glycol to pump is the same rate of the triethylene glycol stream that we have defined before. I'm talking about this stream. Because we are making regeneration to take the triethylene glycol back to this stream, which is triethylene glycol feed. So we want the flow of this stream, triethylene glycol to pump, to be the same flow as triethylene glycol feed, which is 0.5 cubic meter per hour standard ideal flow rate. Now you can find it's already solved, and HYSYS calculated the makeup required to achieve this flow rate. Now we will add a simple pump. Here, the inlet is triethylene glycol to pump, and the outlet pressure, we will define the energy, pump Q, and the outlet triethylene glycol pump out. Here, the outlet pressure is 6,275 kilopascal. We'll find that the pump is already solved. Now we want again to cool down the triethylene glycol coming out from the region column, which is this. So we can do that with the dry gas, this one, which coming out from the absorber. Add a heat exchanger. Glycol will go to the tube, which is triethylene glycol, pump out, and the sales gas go to shell, dry gas, shell out, sales gas, and the tube out, triethylene glycol, heat exchanger out. Go to parameters, delta P 70 for tube, and 35 to shell. Do not forget to deactivate the FT, and go to worksheet. Sorry, I will change the name of this stream, which is triethylene glycol heat exchanger out, to make it triethylene glycol to recycle, and we will know why in a second. Now we want this temperature, the triethylene glycol to recycle, to be the same temperature of the feed stream. So we'll make it 50 degrees Celsius. Now it's solved. You can find that the heat exchanger now is solved. Now, the challenge we have completed the simulation. However, the triethylene glycol that is going to the dehydration, which is this stream, should be the same stream called triethylene glycol to recycle. That's coming out from the heat exchanger, this one. However, they have different composition and slightly different pressure. If we redefine the triethylene glycol feed to be exactly like the triethylene glycol to recycle stream, HYSYS will recalculate all of that, and you will find a new composition for the glycol to recycle stream, and so on. So this will not be the suitable solution. What can we do now? We can use a function called the recycle function. This function will equalize the two streams, which is triethylene glycol to recycle and triethylene glycol feed, by calculating the model many times till finding the specifications and the compositions that equalize both. Before doing that, let's save our model, and now we can add the recycle function, F12 to open the palette. Just try to recycle. The inlet is what is triethylene glycol to recycle. And the outlet is what we want to connect this stream with the triethylene glycol feed. Now it's solved. Go to parameters. These are the tolerance for variances between the two streams. The tolerance for flow, enthalpy, and composition should be minimized. So I'll make this one, and I'll make this one as well. and I'll make this one. Now this stream, which is a triethylene glycol to recycle, is consistent with this stream, which is triethylene glycol feed. The last thing we can do with the model is to check the hydrate formation conditions for the sales gas. Open this stream to do that. Now go to Attachments, then Analysis, and I just make it like that, and I create a new analysis. Here you can analyze a lot of properties for the stream. Go to Dehydration, Hydrate Formation, and add. HYSYS tells us now that hydrate will not be formed in these conditions. Go to Performance. You can find here that the hydrate formation temperature is negative 10.5 Celsius. So now we fulfill the sales gas specifications, which was negative 10 degrees Celsius at 6200 kilopascal. Now we have finished the model. Please take a rest and keep tuned.